Now let's try and look at a numerical example on Regula-Falsi. Two prerequisites. One is, of course, you remember the formula, how we derived it, and also what is the procedure you have understood graphically. Let's implement it now in its entirety. Now the problem on hand is this cubic equation whose root we are trying to estimate. That is x cube minus 9x plus 1. A cubic equation would possibly have 3 roots, but here we are interested in one of the roots that lies in the interval 2 and 3. And what is the criteria for assuming these two values of x for the function? It's very clear that if you put a is equal to 2 in the function, that is in the cubic equation, you realize that the value of the function is negative. And when you substitute b is equal to 3 in the function, you realize that the value of the function is positive. So that is 1. And also what is to be noted here is that when the function has a value minus and plus, that is for x equal to 2 and x equal to 3, obviously the root lies between those two values. And that is graphically depicted over here. You can clearly see that at x equal to 2, the value of the function is minus 9, which is x and y coordinates. And at x equal to 3, the value of the function is 1. So therefore, the x and y coordinates are depicted here. And then the function is actually plotted between those 2 points. And you can see wherever it crosses the x-axis, that is my desired route. That is my interest. How actually I get closer or closest to that is the question using Regula-Falsi approach. So let's try and proceed. Of course, this formula is what we are going to use to estimate our roots, that is roots which are going to be closer to the actual value. And after certain iterations, it becomes practically acceptable because it would be extremely mathematically close to this particular point. So what is the first iteration? Let's look at here. As the procedure is extremely clear to you, what we do, first we draw a secant between x equal to 2 and x equal to 3 points. That is when x equal to 3, the value of y is 1, and when x equal to 2, the value of y is minus 9. We are joining those 2 points by a secant. Or you can simply say a straight line is joining those 2 points, because you can see this is the curve that we are trying to estimate root for in this particular bound, that is x equal to 2 to x equal to 3, and I am trying to draw a straight line between those 2 points. And this straight line is intersecting with the x-axis at certain point. So I'm going to replace my a is equal to 2 or x equal to 2 by the x coordinate of this particular point. That means my next investigation would be by projecting this particular point onto the curve and then drawing one more secant so that I start moving towards the root that I desire at that particular point. So therefore, I have drawn my straight line joining those 2 points. It has cut the x-axis, and I want to know what is the new value of a. Remember the process here. This was my value of a at the inception. This remains fixed throughout. You don't have to worry. And you can see that the value of a is going to shift from 2 to the point where the intersection happens of the straight line with the x-axis. So how did you estimate that particular a? From the standard formula. Remember, f of b minus f of a is what is going to come in the denominator, and in the numerator it is f of b multiplied by a minus b into f of a, just ulta. And of course you get a negative sign in between. And when you estimated that, because you to start with a is equal to 2 and b is equal to 3, and the values of f of b is 1 and minus 9, and when you substituted those here, 1 minus 9 1 multiplied by 2 and minus 9 multiplied by 3, and of course a negative sign that comes, you get 2.9. That means the x coordinate at this particular point is 2.9, but what you started with is 2. So now I'm going to replace a by 2.9, right? So that is very, very important. So therefore, if I replace a by 2.9, what happens to my next iteration? Let's see. See, once I got a is equal to 2.9, what I did, I actually dropped a vertical straight line to the curve, and my new y coordinate would be minus 0.711. You started with minus 9, you can see here, this is minus 9. The moment you did your first iteration, it in fact got reduced to minus 0.711, right? And your a now becomes 2.9, and that's what exactly we have iterated here. You can see f of a was minus 9. The moment we estimated the new a to be 2.9, you can see that the nature of the function, that is the value of y or the value of the function, value of y is nothing but the value of the function, becomes reduced to 0.711. How did we get that? We substituted 2.9 in the function, the definition of the function, and we could get minus 0.711. So that clearly tells you that you are indeed moving towards this particular point, So what would be the next iteration? Now I'm going to draw one more straight line between 2.9 comma minus 0.711 and the fixed point 3.1. So that is going to be the fixed point. So now you can see that the sky blue line, which actually joins 2.9 comma minus 0.711, where 2.9 is your first approximation and minus 0.711 is the value of the function, and the other point remains fixed both in terms of value of the function and the x coordinate, and you are joining those 2 points by a straight line, and you can clearly see that wherever it intersects the x-axis, you get your second approximation. And how do you move to the next approximation? In fact, you will have to again drop a vertical line from the point of second approximation and then draw one more straight line. So that is done as follows. You can see that the point where you got your second approximation, which is you can calculate to be 2.9415. How do you calculate that? Again, it's quite easy. Your f of b and b remain fixed, and f of a in fact moves from minus 9 to minus 0.711, right? Say, because you can see here, you can visualize this. You started with minus 9. The moment you drew the straight line which intersected the x-axis at a is equal to 2.9, that is x equal to 2.9, then what happens? You are dropping a vertical onto the curve, and you can see that the value of the y coordinate is got here to be minus 0.711. So you are going to have your new a to be 2.1 and new y to be minus 0.711. One thing you have observed here, we have consistently using the symbolism a for the other point, because you have to be familiar with this particular formula for only one variable. That means b is fixed, you don't have to worry, and a is the one that is changing every time, and therefore to be consistent with this formula, we are just calling this as the old a and this as the new a. The symbolism remains absolutely intact. Now let's go to the next iteration. Now this is understood. So the first iteration gave us 2.9 and the value of the function to be minus 0.711. Now the next iteration is going to be simple. You are going to draw a vertical from the second estimated root to the curve, and that's what exactly we have done, and therefore you get the value of the function to be minus 0.02147 at the second estimated root, because if I substitute the second estimated root in the function, I get this value. But what is to be observed very carefully is that the value of the function was minus 9, it became minus 0.7, and now it has become minus 0.02147. What is our ultimate goal? the value of the function exactly at that point should become 0, where your straight line cuts the x-axis. If that coincides with that of the curve, then the value of the function is going to be 0. So now we have drawn one more vertical. Now if you join this particular point, that is where you have the second approximated root 2.9415 and the value of the y minus 0.0214 to the point 3 comma 1, you will get your third approximation. So since it's very, very difficult for us to demonstrate it graphically, what we have done is we have said that on the XLS. What you do is you start with this particular function value, and the value of the b is value of the function at x equal to b is fixed. The value of b is also fixed. So this is our second estimated root, and then if I substitute that, I will get my third iteration or the third estimated root, which is almost exactly close to the actual root. The actual root is 2.94282. How do you get this? You can get this using a graphing calculator, but in case you don't have the actual root value, which is not there in a typical examination situation, what you can do is you can see that how much your estimated root is improving. You can see from 2.9 to 2.94 a significant improvement. From that to the next root, the improvement is very, very small, only in the third decimal place. So therefore you can halt your iterations. But of course we know the actual root here, but in an examination you can halt your iterations when the improvement is almost negligible. So let's recollect everything in detail. So since everything is depicted graphically, the advantage is you don't have to do any struggle in order to recollect. So this was the function that is plotted, exaggerated for visualization. And what we are given to understand is that this particular function, that is this cubic function, root has to be estimated between a is equal to 2 and b is equal to 3. And why are we sticking to this symbolism? Because we have given you the formula in terms of a and b. So every time you iterate, a changes, b remains fixed. That's very important. Now you can see that we have calculated the value of the function or the y coordinate for a is equal to 2, which turns out to be minus 9, and b is equal to 3, which turns out to be plus 1. And those are depicted here graphically. And wherever the function intersects the x-axis is the actual root. Now let's come to the next, that is the first iteration. First iteration is all about joining those 2 points by a straight line. And once we join the points by a straight line, wherever it intersects the x-axis, that becomes my approximate root. My actual root is here, and every time I iterate, I cut the x-axis by an equivalent straight line, and I am moving towards the actual root, right? First time when I cut, my approximate root is given by this formula, because here you know f of b is 1, f of a is minus 9, and b is 3, a is 2. When you substitute in the formula, you get 2.9 as your first approximation, or the first root that tells you that it is approximately equal to this the root that you are seeking. But the quality of approximation actually improves as you move towards iterations. What would be the next iteration? How do you guess? You drop a vertical, just like in Newton's method you are drawing a tangent. Here you are drawing a secant. Next, what you are going to do, there also you are going to drop a vertical to the curve. Here also you are doing so. You are dropping a vertical to the curve, and when you did that, you get your function value. And of course you note that it continues to remain negative, because you can only estimate the root when the 2 points are such that one of them gives you the negative value, one of them gives you the positive value. This is the first approximation. Now I can do the second approximation. Once you get the first approximation, drop a vertical, get a point on the curve, because you should always get 2 points on the curve, right? 1 point will give you the negative value, 1 point will give you the positive value, so that you can estimate the next iteration. So having done this, you are again going to draw one more vertical line, sorry, you are going to draw one more line joining these 2 points, so that wherever it cuts the x-axis, you get your root or approximation. That's what exactly we have done. So this can be called the second approximation. Every approximation consists of these 3 process. One is, first have 2 points. One gives you the negative value of the function, one gives you the positive value of the function. Then draw a straight line joining those 2 points. Wherever it cuts the x-axis, that gives you the approximate value. So this is going to be my second approximation. And how do you get it? I require the value of function a, and that we have calculated previously, because you can see the moment you get 2.9, substitute that in the original function and get the value of the function, which is negative, of course. You also know that the value of b and value of function b is fixed, and therefore if you know the value of a and the new value of a, and therefore the new a, if you know, you will be able to calculate your second approximation, and that is what is 2.94155. You have almost moved to the root, right? The quality of approximation now is very, very good. So if you want to have an excellent approximation, go for one more iteration. What is the procedure? Drop a vertical to the curve, and you get the value of the function at that particular second approximation, because this is my approximated root in my second attempt, and for that the value of the function again is negative. And how do you calculate that? Put that in the standard function, you get the negative value. Again you will get 2 points. One has got negative value, one has got positive value. Again you are going to draw one more secant to get your third approximation, and that is shown here. And that, if you join these 2 points, this point and that point, if you join, you will get this particular value. How do you find it out? Again using this formula, that is 2.9427 83277, which is very, very close to your actual root. But in a typical examination, you may not know the actual root because you will not have any graphing calculator allowed. And in such situation, what you are going to do, you are simply going to observe how the values are changing. You can see there is a significant difference between the first and the second iteration, and between the second and the third iteration, the observation or the change in the value is very, very negligible. So therefore, we could halt at this particular point and say that the iterated or estimated root is 2.9427. If you know the actual root, you can always see how your error is actually changing with every iteration. So that also could be changed. But of course, here we have looked at the value of the function. More way to halt your iteration is that the value of the function almost reaches 0. Why? Because you can see graphically when you draw a secant or a straight line between this point and this point, it almost cuts the x-axis at the exact root. The root is a point where the value of the function goes to 0, and you can see that the value of the function at this particular point is practically 0, and it is acceptable. There are two ways of halting your iteration. One is look at the value of the function, which is going to be almost 0, and second one is that the progression of the roots will be very, very minimal arithmetically. That means in terms of numerical value, the change is not going to be significant. So therefore, this demonstrates the Regula-Falsi method. So what you are doing, you are having one fixed point, one variable point, join a straight line, wherever it cuts gives you the approximate root, and then drop a vertical from that to the curve, draw one more straight line, wherever it cuts the x-axis gives you the second approximation. Every time you draw a secant joining 2 points, one giving you the negative value of the function, one giving positive value of the function, you have an approximation. And what are the two rules that you would adopt to halt your number of iterations is that look at the value of the function. It should almost practically go to 0. And secondly, you will see that the observable change between the estimated roots is almost going to be negligible. So let's look at more discussions on Regula-Falsi. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.